Everyone, in this video lesson, we're going to talk about linear regression, which is kind of like the process of making a line of best fit. So let's get started. There we go. So a line of best fit, you guys worked a lot with in earlier grades, specifically grade 9, is a line which best represents the trend in data. And we use it for making predictions. The formal process by which a line of best fit is made mathematically is called linear regression. So in grade 9, here's how generally you guys performed linear regressions. You use certain guidelines. So you tried to have your line of best fit have the same number of points above and below your line of best fit. Your line of best fit should kind of show the trend of the data, should follow the trend of the data. And then you should try to have it pass through as many points as possible. If you try to do all these things, you generally get a decent line of best fit. The thing was, though, this relies on our own, like it relies on you and kind of estimating. And you might have done your line of best fit, but your friend had something slightly different. And then your teacher's solutions had something a little bit different as well. And when you guys found equations using slope and y-intercept after drawing them, it's a little challenging because, again, everyone had a decent line of best fit, but all different. We'd like a way to get the absolute line of best fit that we can all agree on. That involves residuals. So what are residuals? Residuals are the vertical distance between a data point and the line of best fit. And they can be positive, they can be negative, or they can be zero. So I want to do a little visual here, and I might add to this as we go through some things today. So, and I'm going to try to be specific about where I draw these labels on my diagram. So for this first data point here, this point, and I want to say that this line I have drawn here isn't necessarily the line of best fit. It was just one I just created that looked to kind of follow the trend. It's not the line of best fit. But I want to show you how you can, given a line that you think fits the data, how you can calculate these residuals. So R1, this looks to be about 2.6 units above the line here. I'm just going to call it my line of best fit. It might not be the absolute best, but you can see it kind of same number of points above and below, follows a trend, passes through a point. So it does a pretty good job. The next one is below the line of best fit. So its residual is going to be negative. So here we have R2, looks about like negative 2.5 perhaps. This guy's above, and it looks to be 2 above. This guy is below, and looks maybe like 1.3 below. So I'll say R4 equals negative 1.3, let's say. This guy is right on the line, so the residual here is 0. And then this little guy here, R6, looks about maybe 0.9 above. And so those are the residuals. And if this is the residuals for my line that I drew, and if you drew your own line of best fit, I bet we would probably have the same general line, but your residuals might be slightly different. So every line you draw and try to fit to a curve will have different residuals. Here are the residuals for this one. So you should be expected to be able to calculate residuals or estimate them given a scatter plot in a line that's trying to fit the curve. So how do residuals help you get a line of best fit? Well, it turns out that a line of best fit will satisfy 2 conditions: the absolute line of best fit. 1, the sum of the residuals will be 0 for a line of best fit. 2, the sum of the squares of the residuals is going to be a minimum. So what does that mean visually? So you can see if you add up the residuals here, R2, or the ones above 4.6 is about 5.5, and it's only negative 3.8 below. So this isn't perfect. In fact, I might, for this particular, I might actually shift this line of best fit down a bit to balance things out, but it wasn't that bad. But what would the sum of squares be? So visually, it would look like this. So visually, you can make like a square out of each residual. And you can see when you have a big residual, you get a big square. And when you have a small residual, you get a small square. And the idea is and you can add up the area of all these squares. The idea is, for the line of best fit, you want these squares to be as small as possible. Some might be big, some might be small, but their total area you want to be as small as possible. We can actually calculate the sum of these squares. So I could do 2.6 squared plus negative 2.5 squared plus 2 squared plus negative 1.3 squared plus 0 squared plus 0.9 squared. And I could actually get a numerical value for the sum of these squares. So let's just do that for this one. And then you guys have this example to use as you do the same thing in a little task in our next lesson, plus 0.9 squared. So I got 19.51. Just going to double check that. 2.5 squared plus 4 plus 1.3 squared, 0 plus 0.81. Yeah, 19.51 for this particular line. So that's what I got for mine. If I had another friend who drew a similar line, but a bit different, I could see who drew the best line of best fit by calculating my residuals and doing this calculation. And whoever had the lower sum of squares did the best. It has the curve that fits the best. The absolute best will minimize this value. So every different line will have a different sum of squares value. The line of best fit will have the best one. Now that is hard for us to do by hand. And so we have ways for technology to do this for us. But that's visually what goes on when you do a line of best fit. Now I have a blank slate. We talked about this. I have a blank slide here just to remind me to go to a little visual. And I'm going to post the, where are we here? I'm going to post this link on the classroom for you to play around with it. So I'm going to make, this is the PhET simulation, which I usually use for physics simulations, but it's going to be pretty good for ours too here. I might move this guy. Make something like that. Okay, so here's a scatter plot. And I'm going to fit a curve to that. So if I fit a curve to this, I think my curve should have a y-intercept maybe around 4.4 or something, and the slope is positive. I don't know. That's decent, I guess. Let's just leave it there. And I'm going to add the residuals. So you can see you've got lines there above and below showing the residuals, and then the squares, the residuals. So you can see those diagrammed here. And what's cool is now, as you can see, as I change my line of best fit, do you see that the squares are changing and the squared residuals are changing too? And you can see the sum in this little bar down here is going up and down. So, obviously bad, the sum is big, the sum is small, 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 but it's going back up. So maybe something around here is better. And maybe if I played with the y-intercept a little bit too, I could find a sum that did the best. But hopefully you're convinced. Yeah, as you can see, as you change the line of best fit, those squares change and the sum changes, and we want it to be lowest. And I think if I click this, it gives you the best one. Yeah, there it is in red there. It gives me the absolute line of best fit. And I can show the residuals and residual squares for that one too. So pretty neat. Yeah, we're not going to be doing this by hand. We'll get a computer to tell us how this line of best fit is made. But we now know how this is made. When a technology spits out a line of best fit, we know that it's done the residuals squared, and it's found the line that minimizes the sum of those squares. So I thought that was a pretty cool visualization to show you guys. All right. So now that we know how lines of best fit are created, the least squares regression, let's actually just do a couple. So in the classroom, I usually use a set of TI Inspires, but I'll use Desmos and Google Sheets as well. It really doesn't matter what you use. Any spreadsheet program will do. It's just the buttons are a little bit different. Due to distance learning and where we're at now, I'm going to do this along with you guys in Google Sheets. So here we have some data showing students' grade 12 averages compared to their first year university average if they did go to university. I want to just show you guys, we're going to make a scatter plot and we'll just make sure it lines up with this one. So let's head back to our data, and I've got this data ready to go for you guys. So highlight our data. This time the data is entered horizontally. Shouldn't be a big deal though. Insert chart. Insert chart. There we go. What's interesting with this one is that it actually comes up as a line chart, which is not very helpful. We want to change that to a scatter chart. And it's the same graph as the TI Inspire, the one on the handout. It's just the scale's a bit different. But we can see as grade 12 average increases, generally the first year average increases too, which kind of makes sense. We see that as well here, just the scale's a bit different. As high school average increases, university average increases too. So that's basically what the scatter plot tells us. And we could probably say too that there's looks like a moderate to strong positive correlation between high school average and first year average. What if we wanted to make some predictions though? Maybe my average was 81 and there's no data in there for a mark of 81 and I wanted to make a prediction. Well, let's get a line of best fit so we can mathematically make some predictions. So let's use our spreadsheet program and we'll see that we should get the same. This was created using the Inspire. Let's see if we can get that on Google Sheets. And let's also get the R value while we're at it. Okay, so I have shown you guys how to get a trend line. We click on the data, any data value will do, scroll down and add trend line. That'll give us the trend line, and we know how to get the R squared value so that we can find the R value. Now, how do we get the equation for the line of best fit? So once you click trend line, you can see, we're doing linear and it made it blue. Well, let's change, green is nice. You can change the thickness too. But anyway, what you want to, if you want to see the line of best fit, it's under label here. We're going to label it using the equation. And so now we can see here's our equation of line of best fit. It's about 1.17x. And you can see that we're adding a negative here. So it'll be minus 22.5. So where are we here? Let's get, yep, so it checked out. The Google Sheets got the exact same line of best fit as the Inspire did. The equation line of best fit was about 1.17x minus 22.5. That'll be good enough. The R squared value was 0.773. And so our R value, our correlation coefficient, will be the root of that, the root of 0.773. About 0.88. Strong positive or very strong, depending on the scale you use. Now, we knew it was positive because the trend line is increasing. If the trend line was going down and to the right, we would know once we took our square root, we would say R is negative 0.88. But here is strong positive. So you guys now know how to create a line of best fit, get the equation for it, and find the correlation coefficient, the strength of correlation in Google Sheets. And I think that's probably the tool we'll continue using moving forward. But yeah, now that we have our equation, we can make some predictions. So I might just rewrite my equation down here. It was y equals 1.17x minus 22.5. Yep. So here, y is the dependent variable, which was the first year average. And x was the dependent variable, which was our grade 12 average. So we can make a prediction. So let's say somebody's grade 12 average was 82. What can we expect for their university average first year? At least using our data, how can we predict that? So we just plug in x equals 82 and work it out. 1.17 times 82 minus 22.5. So using our model, we can predict their average to be about 73.4 in their first year, using our model anyway. We could also say, what if our students' first year average, what if we wanted it to be 70%? What would their grade 12 average have to be? So we can still use our equation, just solving for x in this case, the independent variable. And you guys have been solving linear equations your whole life, so we don't need to review how to do that. But and you might have different ways of showing it, but I'll add 22.5 to both sides, and then I'll divide by 1.17. So 92.5 divided by 1.17, got about 79. So a student who got 79 as an average in grade 12, according to our model, can maybe expect to have a first year average around 70. So this is actually the level of predictions that you guys will be expected to do. Perform a linear regression using technology, get the equation line of best fit, and be able to make predictions, both finding an x value and a y value. Just keep in mind, the y value is your vertical, your dependent variable, and your x is your horizontal. So that's what you guys should be expected to do after performing a regression. But now, because that we're all using least squares and using technology, we will all have the exact same absolute line of best fit, which is the difference between what we're doing now in grade 9. All right, let's do one more example together. So here we have some data on students' driving test scores based on how many instructional hours they had. So let's make a scatter plot and do a line of best fit. And then we'll come back. So you can pause, get that done. If you want to add what it looks like to your, just roughly what it looks like on your sheet, that's fine. But really what we're just going for here is the equation and the correlation coefficient. But you'll definitely notice something interesting when you create your scatter plot, draw your line of best fit. So feel free to pause and do that, or kind of follow along with me. I have the data here. Question 2. So let's insert a chart. All right, this one came up as a scatter plot. That's great. Click on the data point, add a trend line, label, use equation, show R squared. We've performed our linear regression. We know it was a least squares regression. We just don't need to worry about all the bits and pieces of how they got there. What's interesting about this, and feel free to transfer a rough sketch of this to your handout if you want, is that we expect that driving test scores would increase as instructional hours increases. And you can actually see that trend in the data points, except for this one down here. And this one down here has a massive residual and a massive residual squared dragging the line of best fit. So the line of best fit actually is going down. It has a negative slope. So let me just transfer this equation to our my slide here. So we got negative 0.133. I think it was that. I think it might have been 0.33. Yeah, 0.133 plus 79.8. 79.8. And I'll just erase that. And that was negative, I'll just say negative 0.13 for now. Should be enough accuracy. And I'm just going to make a super rough sketch of what we saw. So generally we had 6 points forming an upward trend, one of them going down, which made our line of best fit. It looks something like that. That's not perfect, but that's kind of what's happening, which is odd. And the fact that that 1 point was so far down gave us a very low R squared value, R squared 0.002. And when you square root that, you get 0.04. And we know because the line of best fit goes down here, that's actually a negative correlation, negative 0. I'll say about negative 0.045. So there's almost like no correlation. And that's really weird. So what's odd about your line of best fit? It's weird because the trend looks to be going up, but the line of best fit is going down. And we almost expect a positive correlation. And the reason this is happening is because we have an outlier here. Now, with one variable stats, we had a formal way to identify outliers. In this particular case with the scatter plot, we don't exactly have a formal way, but I think we could all agree that this data value down here doesn't kind of follow the trend. The student who had 20 hours of instructional time, almost the most out of anybody, had the lowest score. Now, they had a lot of hours and got a low score. There's probably a ton of possible explanations for this result. Maybe on that day that they had their driving test, one of their pet died, or they were very sick, or they're under a lot of stress for one reason or another. We can think of lots of reasons why. Everybody just has a bad day. Maybe it wouldn't be fair to keep her score, his or her score. So, if we had a good reason, if we could say, hey, there was a really good reason why this person had a low driving test score. So maybe if we want to make a model here, maybe it's not really good that we use their score, and we can remove it. So if we can justify removing an outlier, we can do that, maybe get a better model. So let's do that in Google Sheets. What you can do is you don't have to redo your entire thing. You can actually just delete I'm going to highlight those values for our outlier. And if I delete them, it dynamically updates my line of best fit. So that's pretty cool. And what we can see is we now have our line of best fit definitely follows a trend. The R² value is much higher, and we root that, we're going to be into the 0.9s for sure. So we have a strong correlation. So let's get that down. 1.23x plus 66.5. R² was 0.858. And I'm just extremely rough. You guys have the diagram in Google Sheets, but now that our line definitely follows the trend. So our R value now is going to be a very strong positive R value. The root of 0.858, about 0.993. All right, so this example here, and we might look more at outliers and misusing data, but if we can justify removing an outlier and we have a very good reason, sometimes we can do that to improve our model and help us make predictions. So now we probably have a more reliable model about how a student's driving test score would depend on their instructional hours. So what you guys should be able to do after today is understand this least squares regression in the process. Maybe even play around with that app that we did. But you guys, if I gave you a line of best fit, a simple one like this, I'd expect you guys to be able to draw the residuals and calculate the sum of those squares. And in fact, in a task next lesson, I will give you two friends who have two different lines of best fit, and you're going to see who has the best one by doing a calculation like this. So you should understand least squares regression. You should be comfortable using technology to create a line of best fit, get the equation, and get the R value. And then you should be able to use that equation to make predictions. And this is the level of the math that we'll be using for our linear regression. Not too heavy. Plug in an X value, find a Y value. Plug in a Y value, solve for the X value. And you guys also should be able to kind of dynamically change your scatter plot and line of best fit by possibly removing an outlier. And we can see if we have an outlier that we have a justification for removing, it can drastically change the model. So today I have some practice for you. You may want to work through. The next lesson, I just have a task to work through. It's not very heavy. You're just doing the things that we've been doing, basically did in this lesson. And then we have 3 or 4 more lessons to go before we've covered the course content. So that's it for today, guys. Stay well, and hope to see you guys soon.